So, good afternoon. Can you hear me? So, good afternoon, everyone. Of course, it's very nice to be here in this wonderful institute and nice to be back in this meeting. So, the work I will talk about today is again kind of incomplete. It is being done in collaboration with my PhD student, Jensina, who also has a poster on display here. The question that we ask is quite simple here. So we consider a set of rigid polymers polymerizing and growing towards a wall, which is actually trying to move towards the polymers because of an external applied force. And what we would like to know is what is the maximum force that can be exerted by this assembly on this obstacle. So I first start with some biological motivations for this problem. So the basic issue here is collective force generation. Okay, so the two pictures I have shown here, the first one actually shows a cell in the process of dividing, and you see all these chromosomes in blue which have been duplicated and are being pulled by the filaments called microtubules, which Dibyendu talked about, towards the two daughter cells. And in the second case, what we see is an intracellular cargo being acted upon by a number of molecular motors, and the cargo is being pulled in another direction by an external applied force. In both these cases, the central question that we ask is like, what is the net force being produced by all these four generators together, and how does it change with the number? In motors, it's a fairly straightforward question to define, because all I have to do is to look at the velocity of the cargo as a function of the applied force, plot it experimentally or in simulations, and then see where it touches zero. And at that point, I know that my force generators are applying the maximum force that they can, and that I define to be equal to the stall force. So we needed a similar device also in the case of polymers, which I'll define in the next slide. And this work has been motivated by many earlier papers in this field. One of these others at least was Dibyendu was the previous speaker. Right. So I'll just talk a little bit about the structure of microtubules, which Dibyendu skipped in his talk, which is again not too relevant for me, but at least some of the details I'll need. So microtubules are, first of all, they're very, very rigid polymers. So unlike our, the standard picture of a polymer in which you imagine a floppy object wandering all over space, these objects are really rigid rods inside the cell. The persistence length run to millimeters and so on. So they are made of these molecules called tubulin, which are like 8 nanometer in length, and then they are assembled together to form a linear polymer and then wrapped around in a cylinder. So if you look at the cross section, it is like a polymer with a hole in the middle, and the hole has a diameter of like 6 nanometers, while the outer diameter is 12. And so this is the structure, this is the model that we use in our analysis. Okay, so we have these rigid polymers, but then we ignore the hole in the middle because primarily for mathematical simplicity. But then another logic could be that almost only about a quarter of the area of the disk is being used for the hole. So I think it is kind of okay to neglect the existence of the hole. So in a simplified model, therefore, we imagine single monomers making up a microtubule as disks of radius equal to the outer radius of the microtubule. We treat growth and shrinkage of microtubule as a continuum process, which is again not strictly necessary. It simplifies the mathematical analysis. And we ignore this very interesting and fascinating property called dynamical instability of microtubules, again, only for the sake of simplicity. Of course, it can be included at a later stage in the model. So then this is our model. So we have sort of box-like structure in which I'm imagining that I have a large concentration of these monomers, the tubulin molecules, which come together, assembled from one side, and form these linear rigid polymers. And the binding is assumed to be diffusion limited. And once in a while, thermal fluctuations knock off the monomers from the polymer. So I also have a dissociation of monomers from the polymer in the problem. And this is my moving wall, which is being acted upon by an external force and moving in this direction towards the polymers. And it is also being subject to thermal fluctuation. So I give it a diffusion coefficient, which I call dW here. So the wall does basically two things to the polymer dynamics. It obstructs the motion of the polymers because the wall cannot cross the polymers, neither can the polymers cross the wall. So they form reflecting boundaries for each other. In addition, as I'll show a little later, as the polymers approach the wall, the wall also inhibits the free diffusion of polymers. That is pretty clear. The question is it a significant effect or not? So this effect can actually modify the rate of adsorption of the monomers onto the polymer, and that can affect the dynamics of the polymer itself. So to actually check that, we we worked out a much simpler model in which we had an absorbing disk of radius A placed at distance d from the rigid wall here. So we neglect the motion of the wall here. And we just try to see by solving Laplace's equation in steady state with appropriate boundary condition, which I have described here. And then we calculate the rate of adsorption of monomers onto that disk. And what we see is that if the radius of the monomer is kind of the order of the distance between the absorbing disk and the wall, there is a significant effect of the wall on the adsorption to the polymer. Okay? So this can be roughly modeled. So it is like as the distance increases, then of course it reaches its steady value, which is actually equal to 4d8 times the monomer, the global monomer density. But as you approach the wall, as my absorbing disk approaches the wall, you see that there is a drop in the flux, and there is therefore a net effect on the adsorption rate, which can be mathematically calculated. The entire expression is kind of quite lengthy, but it can be, to a fairly good approximation, it can be written out as an exponential with a inverse length scale lambda, which is roughly of the order of 1 over the radius of the monomer. It's like the radius, yeah, I mean, it's only a scale, yeah, exactly, radius of the disk. So this is the model then, and now so what I'll present next is first a set of mathematical calculations in which we derive a lot of quantities of interest and then compare them with semi-analytic as well as fully Brownian dynamic simulations. So to proceed with the model, then what I imagine is I have these two filaments, and this is my wall. The wall is at a distance z. It's being acted upon by this force, and then there are these two gap variables, y1 and y2, which give the separation of the filaments from the wall. So the probability density phi, which is a function of z and all the yi's, depending on the number of polymers I have in the problem, satisfies an equation of continuity in my continuum model. Okay, of course, the wall dynamics is always continuous. I assume that my filament dynamics can also be described as continuous, which it can be done under certain approximations. Okay, so if I write down the currents, this is the wall current and these are the gap currents. And you see that the gaps are actually coupled because of the presence of the wall. The gap currents are not independent of each other, even if the filaments are growing independent of each other. So VW is the terminal velocity of the wall given by the standard formula, and then V of y and D of y gives me effective velocity and diffusion coefficient for the polymer dynamics. I also have to solve this equation subject to appropriate boundary condition, which says first the Z current, the wall current has to vanish at infinity, plus or minus infinity, and then the gap currents have to vanish at the origin, the respective origins of the gaps. So delta here is the size of the single monomer unit, which is not strictly essential in the continuum description, but then to map the continuum rates to, the discrete rates to continuum velocity, I have to use these values. So the gap dynamics is kind of simple in the sense that because the polymers are growing towards the wall and the wall is moving towards the polymer, you expect a steady state in the end. And that is really what we find. So the phi of phi, which is defined as the integral of phi with the wall position integrated out, actually reaches a steady state determined by the standard divergence recurrent relation, from which we can also calculate, see, look, all the gaps are actually identical variables, but not necessarily independent because they are coupled through the presence of the wall. But you can define a single gap distribution, which is now normalized, using which after a few calculations, using the boundary conditions also in the problem, we can define the mean wall velocity. We can calculate it, and that seems to be given by this kind of nice looking expression. So the only non-trivial factor is this integral of my y-dependent, the gap-dependent velocity because of the diffusion inhibition over the gap distribution. So once I have this, I have basically found the gap velocity, the wall velocity. So the next step was to apply this to at least one or two special cases of interest, and we started with the case where I completely ignored the dependence of absorption rate on the gap and have all these rates as absolutely constants, which is the simplest problem you can think of. And the gap distribution factorizes into n independent distributions, and it is all exponential. So we have this alpha factor here, which also depends on the applied force. So you put everything back and you find that this is the velocity of my wall. So this is how the polymers are going to push the wall forward as a function of the external applied force. So there are two factors we can notice here. So one is that the zero force wall velocity, or the wall velocity, any fixed force, it's an increasing function of the number of polymers I have, but it is not increasing forever. It is going to saturate at a certain value. That is equal to the individual polymer velocity as the number of polymers become very large. And then the stall force is the force at which the wall velocity would vanish, and that is a linear function of the number of polymers, and that is just to be expected for this simple constant rate problem. So we also compare this against simulations. So we refer to this lambda equal to infinity model because of this 1 minus exponential minus lambda y factor we put in. So as expected, so these are one-dimensional semi-analytic simulations because we have sort of more control over it compared to full Brownian dynamic simulation. So in this case, I don't have really explicitly the Brownian diffusion of monomers, but rather I have just one-dimensional polymers, like what Devendra described. But the rate of absorption is sort of made gap dependent according to this my approximate formula, and I tune my parameter lambda to actually account for the effect of the wall. So the simulation results agree pretty well with the theoretical expression, and we also looked at the wall velocity as a function of force, the velocity force curve, which is a linear force. Of course, you see some deviations here, which I guess is probably because of we replaced the discrete polymer growth dynamics with the continuum description here. Next slide. So now we proceeded to look at the more general case, and at least for up to 2 filaments, one can still write down explicit expressions even when my V and D are explicitly Y dependent. And the new constants appearing can be fixed by normalization, as well as the condition that the first one actually is a condition that the two gap variables are actually identical variables and should have the same distribution once the other one is integrated out. So that again we compared with numerical simulations, and we see very good agreement. There is not much difference between n equal to 1 and 2, which I haven't fully understood, but maybe it's not such a non-trivial issue. And unlike the constant rate case, we see that the gap distribution actually has a peak here. And this is then the results for lambda equal to 0.5 corresponding to a depletion zone of something like 1 to 2 nanometers, sorry, 2 to 4 nanometers. So this is again the force velocity relation, which again is linear in this model, and we compare with the lambda equal to infinity, that's a constant rate problem. We see that the velocity overall has reduced and the stall force has also reduced, both of which is natural because when you reduce lambda, as you go near the wall, the polymer is feeling the effect of the wall and its absorption rate, and there is a reduction in the rate of monomers coming onto it. So there is an essential reduction in the growth rate that sort of affects the maximum force it can exert on the wall. So, and then of course what we needed to see was that whether the scaling property is still valid, and we see that it sort of still scales nicely. So the stall force for a 2-filament system is effectively very close to twice that of a single filament system. But the question is, does it still hold even if I reduce lambda even further? Unfortunately, at that point, my analytical calculation, the continuum model as well as the semi-analytic simulations become unreliable because the rates actually have a big mismatch between each other. So, yeah. Yeah. What gets worse?
The fit with...
Fit, yes.
Yeah, so wouldn't we expect it to get better with number of filaments?
We do not know. See, as I said, I mean, there is an essential approximation in replacing the discrete growth dissociation dynamics of the polymer with a continuum approximation here. Okay, so that I'm not sure actually gets better if we have the number of filaments large, right? No, we do not know that. Okay, I'll hurry up now. So therefore, to understand what happens when lambda is much smaller or when the depletion zone in front of the wall is much larger, we actually resorted to full Brownian dynamic simulations, which have not been completed, but we have like 2 preliminary results I can show here. So in this case, we are sort of changing the radius of my disk of the polymer. So between 5 nanometer and 10 nanometer, if you actually look at how the start force changes, and you do see a difference. Okay, so in 5 nanometer, it actually scales with so for 2 it is twice as much as 1, but here of course it is reduced. Okay, So we believe it is actually an effect of this diffusion inhibition showing up here. Just to confirm that, I mean, maybe in the other case, the large lambda case also, maybe there could have been like sublinear corrections which we could have missed in the simulations. We also did a 1 over lambda expansion and checked this by expanding the wall, the gap distribution in inverse powers of lambda. And then we do a standard analysis and we completed this, and we found that what we found is that actually the 1 over lambda doesn't reduce the stall force, but it doesn't do anything to the scaling itself. At least, therefore, in the leading and the subleading orders, we find that the scaling of stall force, the number of filaments still holds. Of course, that still leaves open the question of when higher order corrections are included. I mean, we still do not know that. Okay, so I'll summarize it here. So what we looked at was a problem when polymerizing filaments pushing against a wall against an external force, and we wanted to know what is the maximum force generated by the filaments. And what we find is there are actually two regimes. When the radius of cross-section of the polymer is close to the size of my monomer, then of course there is a linear scaling. Otherwise, we expect or we suspect a sublinear scaling there, but it has to be confirmed by more simulations. Ongoing work is described here. We of course have to extend this to even larger values of n. We would like to study the effect of weighting the spatial separation between the filaments, which will include explicit diffusive coupling between the filaments. And then finally, we should of course like to go on to complete microtubules with all their structure. And don't forget the poster and thank you.
Unfortunately, we've run out of time for questions, so